last unit is the third day's video for the extra topics chapter for Physics AP. And in today's lesson, we're going to go over just 3 more pages, finishing up our work with the photoelectric effect. Today we're going to look at something called stopping potential. And the key thing about stopping potential, what makes this kind of item what it is we're going to take the battery and we're going to wire it in reverse. Okay, so I've got my battery, which we've traditionally been using to kind of make the electrons go even faster once they're free, but now that battery is wired in reverse. It's going to be wired backwards. So instead of trying to speed the freed electrons up, we're actually going to slow them down. Now this particular wavelength, this is good news. This is above cutoff. These are good photons. Okay, so they're more than capable of knocking some electrons free. In fact, I've got it running here at 450 nanometers, and it doesn't even really matter what the intensity is. I can bring this intensity down to maybe 50%, right? These are good photons coming out of that light bulb that are definitely knocking the electrons free. Some of them come out a little faster than others. Those must have been ones near the surface. And other ones are a little bit deeper, so they're a little bit slower when they come out, but they're definitely coming out. We can see that on the current, on the ammeter there. Okay, and right now my battery is not set up to speed them up at all. And I could use the battery to speed things up, right? I could go and put a positive voltage on this to make them go even faster once they come out. But no, I'm going to actually take this battery and wire it up backwards. So you can try this out, right, if you're experimenting with this on your computer. And if I go with a negative 1 volt battery, so it's wired in reverse, this is a negative plate over here now, trying to repel the electrons that were trying to fly over to it. And this is a positive plate saying, all right, hey, I'm going to attract those electrons back. That creates an electric field in there, a push on those charged particles that's going to make them go back. And you can see them kind of bubbling up and then just making their way back. It's kind of cool watching the actual kind of motion of them. Okay, what can we put in our notes here? Well, we've definitely got, a positive plate here because we've got this battery wired with its positive end connected up to that positive plate. And we've got the negative end of the battery here making this plate there negative. Now, electric fields are generally warnings about what would happen to positive charges like protons. We're not using any protons in here, but if we were, they would get shoved to the right. So officially, it's kind of a physics 12 thing, electric field, that warning about force would be going to the right. We're playing around with nothing but electrons, only electrons. So they actually receive a shove that's in the opposite direction to the warning from the field. So this will be the direction every day here for the force on the electrons. So for negative charges, again, they get pushed in the opposite direction to the field. And what you can see just from playing around with that little animation there is it's kind of like there's this crazy no-go line where they're not allowed to go past, right? I don't know if that's officially what it's called. I'm going to call it that, right? So this is the no-go line right there. So you cannot go past that spot. They're just going to get shoved back towards that positive plate. So let's just put in a couple little notes here about what we're seeing happening. First key point, the battery. Okay, that battery we can wire up either forwards or backwards. First key point, unlike the photons that are flying in there, right, trying to knock the electrons free. To knock an electron free, you need a good photon, right? So the photons matter. But the battery, unlike the photons, does not affect how many electrons are knocked off the metal. It can't control that. I'm just going to finish this little note here. Battery doesn't affect how many electrons are knocked off the metal. Okay, so let me demonstrate that for you. If I play around with the little app here, I can see the electrons getting knocked free. Sure, they don't make it to the other side, but if I change this battery around, I don't change the number that are actually getting knocked free per second. I could change whether or not they're going to make it, but it's still the same number that are bubbling up off the end of that negative plate there. Well, it's not now a positive plate. Okay, but what can the battery do? Okay, it can't affect how many get knocked off, but I'm going to say this. The battery can, however, attempt to stop and push the electrons back. Now, one of the things I noticed when I was looking at this is that some electrons, they make it all the way out to kind of the middle of this little animation, and other electrons, they're barely making it out at all. They barely make it out, and then they go back. Okay, so what's the deal with that? How come some of them seem to come out with such slow speeds, such small kinetic energies? They get pushed back fairly quickly. They don't go very far. And others, well, they make it a little farther out before they get pushed back. And then there's a few that, wow, they make it the farthest, but the battery in this particular setup still manages to push them back. So think that through for a minute, right? Why do some electrons seem to manage to get a little farther, and others, well, they barely come off the surface? Okay, maybe you know the answer. Here it is. Some of those electrons that we're knocking free are knocked from deep inside the metal. And those good photons, that 450 nanometer wavelength, yeah, it's enough, but only barely for those deep, hard to liberate electrons. So the reason for the fact that some get turned back a little bit quicker than others, well, they came out slower, right? Didn't take as much to push them back. So last little point here, the slower electrons, that were deeper in the metal, in other words, they had a larger value for the work function. They had a larger phi. So those slower electrons get turned around first. So that deep electron thing always causes a little nuance to the story where you're looking at it going, what? Why is it like that? And it's just an issue where some of those electrons barely make it out because they were a little harder to pull free from the metal. They were a little deeper. Okay, let's do some more of these critical thinking things, right? This is the good part of physics where you get to actually kind of think about how is this actually going to play out. So for this page here, I've got that set up of 450 nanometers, light bulb's on half bright, my battery's wired backwards. Yep, okay, I can see that there. It's all good. And now what I want to try to do is graph current. So that's really asking how many electrons are successful versus battery voltage. What does it look like? So if I put my battery at, basically around 0 volts, I can see I've got this current of 0.026. So those photons are knocking them free, and the electrons are just making them go faster when they finally hit the plate, but not really affecting the current here, right? Not in any big way. So if I go and turn this current or this voltage up even higher, okay, yeah, that battery's making a really strong force now, big electric field in there, but look at the current. It's still 0.026, right? All right, but now if I start to go back into the negatives, this is where it gets interesting. If I start putting that battery in reverse, you might think, oh, well, it won't stop them for a while until, you've reached that point where they can't get there. But what about the electrons that aren't coming out very fast? If I go even to just negative 0.2, some of the electrons are still making it, right? But some of them are actually getting turned around, right? They're not quite going all the way to the end. Like, look at these ones. They're getting turned around pretty early. And others go a little bit farther. So the current's dropping off. These deeper electrons are already becoming unsuccessful. But the surface electrons, they're actually coming up pretty nicely. Okay, so now I'm going to go back with a little more negative voltage. Just try to adjust that smoothly there. I've got just barely any current flowing. So some electrons are still making it, but many of them, in fact, most of them are now getting turned back. And then if I turn that voltage up to even bigger negative values, then all of a sudden the current's down to 0. So it doesn't all stop at once, right? You end up stopping the easy electrons first. And so the graph for this of, how much current have you got versus battery voltage, looking at this graph, right? We've got a forward wired battery here, right? So positive battery voltage. We've got a negative battery voltage here. I'm going to draw this graph several times. If I was to look at blue photons, what I find is there's a certain amount of current, and I can make that battery go forward, 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 and it doesn't change the current. And at first glance, don't copy me here because you'll be wrong, you might think, oh, well, if I go with negative voltage, I'll be fine until you reach some potential, some voltage value where all of a sudden it doesn't work. But because of the fact that there are those deep electrons and some are harder to get out than others, what happens is as you start to go into negative voltages, you see this current drop off in kind of a nice smooth manner until finally even the surface electrons can't make it out. Now, what if instead of using blue, what if you'd used purple? What would that look like? How would the graph be different? So purple, if blue is above cutoff, so is the purple. Now you might think, oh, well, it'd be the exact same current. Well, actually, purple photons are a little stronger, so they could knock free even deeper electrons. So they'll actually be typically a little more successful. You'd have a better current with purple than you would with blue. Let's see if the animation agrees, right? So if I go with 0 volts, get that back to 0. It's hard to adjust. There we go. So at 0 volts, I've got decimal 0.026. I suspect if I go purple, I'll actually see this current grow a little bit. Yep, decimal 0.061, because I'm able to knock free deeper and deeper electrons now. So all of those photons seem to be statistically more successful. It still has that issue, though, where if I start to go to negative voltages, I'm going to see the current drop off until eventually there's nothing, right? So at some point, there's enough voltage that you can stop all of those electrons from making it to the other side. If you were to go to something like a turquoisey color, maybe that would be in here. And it also would see that kind of angle drop off. And then here would be a voltage with turquoise that, not a single turquoise photon can actually knock an electron free. And then there's this like cutoff frequency color, maybe it's somewhere around green. And then pretty quickly, you're going to see that drop off. So on the right-hand side of the page, the story's pretty flat, because if the electron's out and you're not trying to shove it back, it's going to make it. And putting a positive voltage on doesn't change whether it makes it successfully or not, just changes the impact speed. But what I'm seeing, as you kind of look at this graph here, purple's got this intercept that's farther to the left. So maybe I'll make a little note. How about we say this, that a larger back voltage, these are back voltages, larger back voltage is necessary to stop electrons freed by purple light. So purple light requires a stronger backwards voltage. Let's just see if that actually works. So with purple, where do I have to go dialing back my voltage in order to stop the current? Somewhere around negative 0.4. Okay, maybe I can go even a little bit higher. 0.45, yeah, still have it at 0.45. So pretty big backwards voltage. It's starting to drop off here now. Just trying to find, oh, there it is. Almost no voltage here now. How about, yeah, getting pretty close to nothing. Okay, so somewhere around, is it 0.6? Maybe 0.7. Yeah, by 0.7, I'm just about down to no current at all. But if I want to go and take a look at maybe blue light, which is technically above cutoff, that 0.7, that's way more back voltage than I need. Even 0.6 is enough. 0.5 seems to be around the backwards voltage for that color, where I can stop and turn them around. Okay, I'm almost down to 0 amps there now. Okay, and then for the cutoff frequency, which is somewhere down around here, you'd be like barely able to put any backwards voltage on this at all, right? So maybe decimal 0.3. So they're slowing down and they're just kind of making it to the edge there. So a different stopping voltage in order to stop them for different colors of light that we've got. Okay, but it is kind of neat the way this graph is angled on this side. At first glance, if I hadn't thought about deep electrons, I would have figured it would have been like, oh yeah, you'd be fine, and then dropping off like that. But it doesn't actually do that. It has that angled appearance because some electrons are a little tougher to knock free than others. So maybe we'll throw that in. I mean, pretty much every time there's a little nuance to the graph, it's about that issue of deep electrons. So I'm just going to leave a little last note in here on that. Remember, not all electrons leave at max velocity. Only the surface ones would, right? So deep electrons, they have a larger work function. It's tougher to get them out. They're going to end up with a smaller leftover kinetic energy. Deep electrons get stopped first. They're just not going as fast. So even a small negative voltage will start to slow them down and stop them. Okay, let's just try a little numerical example here. What is the stopping potential? In this example, if the wavelength of light is 450 nanometers and the work function is 1.5 eV, it's pretty common to measure work functions in electron volts. I'm actually going to split this page up kind of into 3 just to make room for the calculations that I'd like to do with you here. First of all, it's nice that they said the wavelength was 450. Neat story. I'm going to need frequency. So V is equal to lambda F for these photons. It's light, so I can go 3 times 10 to the 8 for the wave speed. The wavelength, 450, 10 to the negative 9, and then I can go and calculate the frequency. And so the frequency for that light, that's just more useful for doing this quantum mechanics stuff here. 6.67 times 10 to the 14 hertz. Okay, great. Now let's go and find how much energy you've got from a photon. This is one side of the photoelectric effect equation. I'd be multiplying by Planck's constant. H is just a constant that you can go and look up, and you can figure that out. I just want to show you options for writing this down. So this is the energy of that photon coming in, 4.42 times 10 to the negative 19 joules, which, by the way, if you convert to electron volts, and I'll let you look at the first page, or sorry, the first page of the second day to look back and see the conversion, that ends up being 2.76 electron volts. It's just a nicer way to say it. So electron volts are very tiny amounts of energy. Okay, now they've mentioned the work function. They've said that to knock that electron free, at least the easiest electrons, it's going to cost you 1.5 electron volts. Again, you can go back to the first page of the last lesson and you can see how to change this over if you're not sure. But when you change this to joules, that ends up being 2.4 times 10 to the negative 19 joules. I'm hoping to convince you that electron volts are actually a more convenient way of actually talking about energy. It just doesn't have to have such small numbers. All right, thinking about the photoelectric effect equation. The photon energy comes in. Actually, we found it right here, right? 4.42, 10 to the negative 19. That hopefully is enough to pay for the work function. 2.4, 10 to the negative 19. Oh yeah, it is. 4.42 is way better. And then you'll have some leftover kinetic energy. Okay, great. So it looks like in this story, if I subtract, because I have the values I need, I mean the HF energy is over here on the left, and the work function's right up above you there. If you subtract, you can see that the easiest electrons to knock free get knocked freed with 2.02 times 10 to the negative 19 joules. Which, if you're willing to talk about it in terms of electron volts, this could be super handy. Doing that conversion, it's 1.26 electron volts. So just options there, right? The green stuff is optional. Now, how do you stop electrons that are going that fast from getting to the other side? This is electrostatics from like the 5th unit of Physics 12. You can say those electrons have some EK, and I want to turn them into some EP, some potential energy. And in Physics 12, we saw that you could take the size of the charge, hey, that's the charge on an electron, and multiply it by a voltage between those parallel plates. For parallel plates, that was the easiest way to find out how much energy we're talking about. We want to store that energy kind of as that voltage. And you can now throw the numbers in. You could say, okay, 2.02 times 10 to the negative 19 is equal to charge for an electron. You can look that up. 1.6, 10 to the negative 19, and then a voltage. And that voltage ends up being 1.26 volts. Now, it would actually have to be backwards. You'd actually need negative 1.26 volts. Otherwise, you'd make the electrons go faster, right? You have to wire it in reverse. And notice this. It's the exact same number that you see when you talk about the kinetic energy in electron volts, right? That's why we like to talk about electron volts. It's just a super convenient way of doing this. So that would be the minimum voltage you'd need to stop all of the electrons, including the ones that were the easiest to come out, that come out the fastest. If you had a slightly smaller negative voltage, you could stop the slower electrons, but you'd need that much backwards voltage to stop the fastest ones. Last thing we're going to look at, it just kind of fits in with what we're doing today, is something called the Compton effect. It's an issue that we're supposed to take a look at for Physics AP. And we're going to look at the issue, and then I want to look at it a little bit deeper and go, why? Why did they want us to do this for Physics AP? So the Compton effect is something that happens when photons collide, essentially elastically. There's no sound. You don't hear this happen. They're going to collide elastically with electrons. And when they do, they're going to abide by conservation laws. They're going to conserve both momentum. Momentum's your best friend for collision, so that's always true. And they're going to conserve energy. And it's that last part for why this is included in the Physics AP curriculum. So here's the story. It kind of looks like a Physics 12 story with like a cue ball about to hit an 8 ball, and then they go scattering off at a couple of different angles there. It's a two-dimensional collision. So this incident, this incoming photon, a little purple wiggly photon wave, that's like the cue ball coming in, and the target electrons like the 8 ball. And then when they collide, they're going to leave in different directions. They don't add up to 90 degrees, by the way. There's no nice rule like there was for, playing pool. But they are going to abide by all of the rules for conservation of momentum and energy. So when that electron leaves, it's going to end up with some momentum to the side. But looking at it also, it looks like this thing is going to have some momentum in the y direction. And that means that if it goes up because it got kind of struck at an angle, then the light, the little beam of the single photon of light, it actually has to go down a little bit. There has to be negative y momentum, right? That way, this thing can conserve momentum up and down. Now, just like the 8 ball in our billiard ball questions, this thing has no kinetic energy at the beginning. Okay, it's just sitting there at rest. But there's definitely some kinetic or some energy for that photon here as it comes in, right? There's some HF for that photon as it comes in. Now, I'm noticing that the recoil electron, it does have some velocity. And this is the reason why they wanted to include this in Physics AP, okay, because there's kind of a neat little issue here. So I'm just going to put this little note in. This is the big thing for why this is in this part of the course. Since the electron, okay, that's the thing that was struck. Since the electron receives some EK, it's going to take some kinetic energy, right? It takes some energy out of the story. In fact, let's say this, it receives some EK from the photon. Since that's true, the photon must lose energy. Okay, well, how does it do that? If this was a billiards question, the cue ball would slow down, right? Just 1/2 mv squared. If you can't have enough energy there, or the same amount of energy, you have to slow down. But the photon can't. This is why they've put this into the curriculum here. They wanted to talk about this because the photon, okay, let's talk about it. This is the critical part here. The photon sees a kinetic energy drop. EK drops, but its speed cannot drop. It's light, right? It has to stay at the same speed. So the velocity is constant. 3 times 10 to the 8. How does it actually go about losing energy? And the answer is it changes color, right? If you think about just good old E equals HF, for that photon, in order for the energy to go down, Planck's constant's not going to go down, so the frequency goes down. Okay, so the frequency decreases. And since frequency and wavelength are kind of inverses to each other, right? You have V is equal to lambda F, V is a constant, and we just saw that the frequency went down, so the wavelength's actually going to go up. Bigger wavelengths are less energy. So the frequency decreases, the wavelength actually increases. It gets, for the lack of a better way of saying it, it gets redder. Right? It becomes more red. If it was a purple photon, maybe it becomes blue. If it was a blue photon, maybe it becomes green. And it's going to go to a color that's a little bit lower. So this is the issue right here that the advanced placement curriculum really wanted to focus on, saying, okay, what's happening here? The photon has to give up some kinetic energy. Yeah, it can do that, but it doesn't do it by slowing down. Can't slow down, but what it can do is change its color. And so as it bounces away, it's actually going to bounce away with a slightly different color. Last thing, X-ray production. If you were to have to go to the hospital because you'd fractured a bone and they're going to take an X-ray of it to just see where the fracture is, they need a way to produce these X-rays to then aim at your body and then expose with a little sensor to see those pictures of the bones in your body. And they actually do it with this method of producing X-rays. It's a German word, and it basically means breaking radiation, right? Bremsstrahlung. I'm probably not saying that correctly. And it's just all about radiation that happens when the electrons break. Okay, so kind of the English translation of that would be breaking radiation. The key thing here is energy is conserved. And when I say that, what I'm basically saying is we're going to use energy to find the answer, and it'll be easy, because that's what conservation of energy is all about. So the actual X-ray tubes that they use in the hospital X-ray machines, they have 2 metal plates, a cathode and an anode. And we start off with some electrons. Okay, so these are some electrons here that are going to get launched really fast, okay, with some voltage. Okay, so there's a big, huge battery, right, that's actually going to be applying a voltage here. So I need to have my negative end connected here, my positive end connected there. and I'm going to launch some electrons super fast. So along the way, right here, they're going to be going really quick. They're going to be actually gaining some speed because of the battery. And so we go from, it's kind of like a physics 12 parallel plate story. We go from some electrons that are just originally coming off that negative plate. We can boil them off like we talked about in physics 12 with a heater. And then we're going to accelerate them like crazy, pick up speed, and then they're going to strike this metal plate. And then when they do, as they stop, the energy has to go somewhere. And what we end up doing is creating photons. They're not photons that are red or green or blue or purple. They're actually way more energetic than that. They're actually going to be some X-ray photons. And the equation to figure this out, it's actually really, really easy. We start off back here with this parallel plate story. So it's got potential energy. And then it's going to get converted to kinetic. And then it's going to get converted into photon energy, into light energy. And so the story would say, oh, okay, well, I've got potential energy from the plates, and from the 5th unit of physics 12 that we did, we said, oh yeah, that's how you can find the energy from some plates. It's the size of the charge multiplied by the voltage on the plates. That gets converted into some going fast electrons, okay, into some 1/2 mv squared for some electrons. And then those electrons crash, they break, they give up that energy and that Bremsstrahlung, that breaking radiation, in the form of some photons, some X-ray photons. So that gets converted into HF. Now, from a hospital point of view, you really don't care about those electrons. They were only around for a short time in the story. You just want to go from that voltage on the plates and then eventually have X-rays come out. So we usually skip the middleman here in the hospital calculations, and we say, oh, okay, let's take some electron charge. So that's the charge on an electron, and we'll use a big voltage, thousands, tens of thousands of volts in most cases, and then we can go and create some X-rays. And that would be the equation that the hospital staff would use to try to figure out what frequency of X-rays would we actually have that are being involved. It's just conservation of energy, and it's kind of like good old electrostatics, but they're electrons that move as they stop. They can't just, have the energy go nowhere, so it actually creates some X-rays that you can aim at the patient. And that finishes up this kind of 3-day set here for the photoelectric effect and things that are really similar to it, like the Compton effect and the X-ray production. And then the next video, we're going to start to talk about black body radiation.